Hello everyone, I welcome you all to Physics Wala, and in this session we are going to discuss the next part related to our very interesting chapter, which is General Organic Chemistry, or we can say some basic principles as well as techniques of organic compounds. Now we were talking about the basic electronic effects. We were discussing about the inductive effect and how these effects are going to work. In case of inductive effect, we already know that the entire effect is going to work through sigma bond, and that creates just because of the difference in electronegativity between the carbon as well as any other type of a group or atom which is attached to carbon atom. Now in this particular session we are going to discuss about the next part related to the particular section, and basically in this particular part we are going to be more focused on the analysis of resonance, as well as we are going to talk about the resonating structures. Then we are going to discuss the application part related to resonance, as well as one more effect which is associated with the phenomena of resonance, that is known as mesomeric effect. I hope this part is clear. So let's start with the basics of resonance and how this effect is going to work in case of organic compounds. Now if I talk about the first part, first of all let's try to decode what is the basic analysis of resonance, in which structure you can see the phenomena of resonance. So the phenomena of resonance we already know from some basic parts of inorganic chemistry in chemical bonding, that there are multiple structures which are capable to elucidate or explain the structure of a particular atom. In that case, multiple structures are going to exist. For example, I am taking the example of organic compound, which is a very well known compound. Now if you know this compound, you know that this compound is actually known as a benzene, which is C6H6, and this part is benzene. I'm only using the bond line notation here. So in this particular case, you can see that these double bonds, they can actually change their position and another structure can be easily formed. So this is the second structure. Now if I look at the structure of benzene originally, I can say there are 3 carbon single bond carbon and there are 3 carbon double bond carbons. Now I need to observe that if I am looking at the structure of a benzene, I can say that 3 bond lengths should be carbon single bond carbon, and remaining 3 bond lengths should come out as carbon double bond carbon bond length. But after the actual analysis, in the experimental analysis, experimentally we found out that each carbon carbon bond length, experimentally it was observed that each carbon carbon bond length in this particular case, they are exactly same. They are exactly same. If I talk about the next part, the bond energy is exactly same. So what does it say? It says that these structures are basically some of the part of the actual structure. These are not going to define the actual structure. So in this particular case, something is happening. Bond is changing its position. Pi bond, mainly pi bond is changing its position so that you can get these two structure. If I talk about the actual structure which can explain the entire properties, so you can say that it actually looks like this. It means a double bond is traveling inside all the carbon atoms. That's why we have only single type of a bond length. So we need to understand what is the basic idea of resonance and how different type of structures are capable of showing this type of phenomena. I hope the basic introduction is clear. So let's start with the first part, which is the basic definition as well as analysis of resonance. And we can say when a molecule or a particular ion cannot be represented by a single Lewis dot structure, as you can clearly see in the example of a benzene. In that case, more than one structures are needed to represent all the properties of these structures, and these are actually known as resonating structures. These structures are known as resonating structures. Now if I'm combining all these structures, so the combination of all these structures, all the resonating structures are actually known as resonance hybrid, and this phenomena is basically known as resonance. I hope this part is clear. I hope this entire part is clear to everyone. So you can say that this is the basic idea of resonance. You can say that each type of resonating structure is also known as a canonical form. So if I talk about the resonating structure, I can say it is nothing but also known as canonical form. It is also known as canonical form. Okay. Now the average of the entire structure, which actually explain most of the properties, average of all the structures which explains all the properties, that type of structure which can explain all the properties and which is the average of all the canonical forms or all the resonating structure, is actually known as your resonance hybrid. And this resonance phenomena is actually the most important phenomena whenever we talk about the electronic effects. I hope this entire part is clear to everyone. Just have a look at it. You can note down the definition also if you want, but this is the most important phenomena. Okay. So in this particular case, first of all, we have to understand what is the basic idea of resonance structure, how we can classify different types of conjugations, different type of structures which can show the phenomena of resonance. Then we need to understand how to write down the resonating structure and how to decide the stability of a particular resonating structure. That is the basic introduction part related to resonance. Okay, so let's start with the first part. If I talk about the basic characteristics, if I talk about the basic characteristic features of resonance, I can simply say the resonance structure should differ only in the position of electron, not in the relative position of atom. There will be no change in the relative position of the atom. We are going to look at each and every example why I am saying all these things, but understand that this entire part only explains that bond is going to change, the shifting of bonded electrons is going to change, and mainly in this case, always remember pi electrons are involved. Mainly pi electrons are involved. Position of the atom is not going to change. If the position of atom is changing, definitely that is a different type of isomerism, which is actually known as a tautomer. That part we are going to discuss in the isomerism part. But understand, in this particular case, only the relative position of the pi bond or pi bonded electrons are going to change, but not the position of atom. In the same way, the number of unpaired electrons should be same in on the canonical form. So wherever I am writing any type of structure, the actual number of unpaired electrons, they are going to remain same. There will be no change in the number of electrons. That is the next characteristic feature of resonance. I hope this part is clear. Now moving on to the next part, we can say through resonance the electron density in the molecule becomes uniform, just like the case of benzene. So earlier 3 double bonds were present in different locations, but whenever we are writing the canonical form, you can see 3 sigma bond and 3 pi bond. But if I am writing the actual resonance hybrid, I can say that double bond is partially present in each and every carbon atom or carbon-carbon bond. It means that talks about the uniformity of the structure. It means through resonance, electron density in the molecule becomes uniform. Due to uniformity of electron density, the extra stability of the molecule increases. The molecule is going to get some extra stability, and that part is going to stabilize the entire molecule. Hence, the phenomenon of resonance is a stabilizing effect. Always remember, always remember that this phenomena of resonance is nothing but a stabilizing effect. I hope this entire part is clear. I hope this entire part is clear. This is the basic idea about the analysis of resonance. Always remember, this entire part is going to be stabilizing effect. Now, if I talk about further more about the characteristic features of resonance, we can say the most stable resonating structure contribute maximum to the resonance hybrid, and less stable resonating structure contribute minimum to the resonance hybrid. Just note down each and every point, because after the analysis of the resonating structure, we will get to know that which structure is going to contribute more and which structure is going to contribute less in the resonance. I hope this entire part is clear. Each and every point is very easy to understand. If you are like understanding this phenomena first time, you may find like certain points which are quite difficult, but after the structural analysis you are going to find it very easy, and this is the easiest phenomena in the entire electronic effect, trust me. Okay, moving on to the next part, if I talk about the resonating structures, so you need to look at the resonating structure, in which particular structure you are going to see the phenomena. So first of all atoms participating in resonance must be sp or sp2 hybridized. This is the most important part and mostly works in carbon atoms, because we are dealing with organic compound. Definitely we are talking about the carbon atoms, so mostly carbon atom should be sp or sp2 hybridized, then only you can see this type of phenomena which is working. In the same way, the parallel p orbitals overlap to each other. So basically, if I talk about the phenomena of resonance, for example, we have a carbon, double bond carbon, single bond carbon and double bond carbon. In this particular phenomena, you can see that pi bond, if I am representing the pi bond, I can simply write down the structure as C sigma C sigma C sigma C, like that. So in this particular case, they are connected with each other through pi bond, and these two are connected with each other through pi bond. If that is the situation, you can shift the entire cloud and you can say these two can actually interact and they can easily form pi bond. So they should be parallel to each other so that they can participate in the phenomena of resonance, just like the phenomena of benzene. Every p orbital is actually parallel to each other and they are perpendicular to the molecular plane. So that's why they can easily participate in the phenomena of resonance. I hope this entire part is clear. Now, moving on to the next part, molecule should have a conjugated system. This is the most important part. So we need to understand what is a conjugated system and what are the classifications of conjugated system, so that we can write down different type of structures. Parallel p orbital systems are actually known as conjugated system. So in that case, a very simple phenomena is, if I talk about the parallel p orbital systems, they are actually known as conjugated system. Now in this case, if you look at this entire part, this carbon is sp2 hybridized, this one is sp2 hybridized, this one is sp and this one is sp. So first of all, first condition is satisfied, which is sp2 sp2 sp as well as sp. Next part, in this case, conjugated system means generally we can say alternate double bond system. Generally we say, in general, this is alternate double bond system. Alternate double bond system, or you can say alternate, we have alternate pi bond system. So you can see pi bond is there, then sigma bond, then pi bond. So alternate positions are occupied by the pi bonds. Definitely it's going to show the phenomena of resonance. But if you look at the structure, double bond separated by single bond means pi bond, then sigma bond, then sigma bond, then pi bond. This is not the alternate system. So in this case, resonance is not possible. In the same way, let's talk about certain more examples. If I talk about this entire part, pi bond separated by single bond, then pi bond means conjugated system is present. Definitely it's going to show the resonance. But in this particular case, again you have a pi bond, then sigma bond, then again sigma bond, then pi bond. So there is no conjugation in this particular case. So definitely no resonance in this particular phenomena. Just like that, if you talk about this system is actually alene type system. In case of alene type system, you can see this part is sp2, this part is sp and this part is sp2. So condition is fulfilled about sp and sp2, but again they are not present at the alternate position. Double bond is again followed by double bond. So in that case, there will be no resonance. And same with this particular case, because you can see sp3 hybridized carbon here as well as sp3 hybridized carbon here. So there will be no phenomena related to resonance. I hope this entire part is clear. I hope this analysis is clear. Very easy to understand. Very easy to understand. Now, if I talk about the conjugated system, let's talk about the types of conjugated system. Let's talk about the types of conjugated system. So first of all, we are talking about the alternate position of the bonds. Whenever you have alternate position of bonds, then you can see there might be a chance that we have the conjugated type system. And the first one and the basic one in that particular case is negative charge electron alternate to the pi electron conjugation. Or you can simply say double bond separated by single bond. You can say double bond separated by single bond and then lone pair or negative charge. Okay, lone pair or negative charge. First of all, we are starting with the negative charge, so I can say that I am writing only then negative charge. Okay, so first of all, let's try to decode what is the basic idea of these type of system. And before that, I want to mention one thing. If I talk about the types of conjugated system, there are different types, multiple types of conjugate systems are present. How to decode that particular part? You can say first part is a double bond separated by single bond, then double bond. Very classic type of system, just like the benzene structure. Second, you can say that we have a double bond separated by single bond, then we have negative charge. Next part is a double bond separated by single bond, then we have lone pair of electrons. Okay, in the same way, you can say we have a double bond separated by a single bond, then positive charge. Then we have negative charge separated by single bond, then positive charge. You may have lone pair separated by a single bond, then positive charge. So these are different type of systems which can show the phenomena of conjugation. This is the basic idea. And first of all, we are picking the system which is double bond separated by single bond, then negative charge. How this delocalization is going to occur? Delocalization means change in the position of pi bonds, which is the delocalization. Now, if I talk about the first type of system, we have a double bond, then separated by single bond, then negative charge. Okay. That is the basic idea. So you can see this type of system is going to be the conjugated system, because this negative charge can be converted, easily converted into pi bond, and this pi bond can be easily converted to negative charge. So you can write down the structure here, which is it becomes CH2 negative, then we have a CH, then double bond CH2. Now, one thing from this phenomena, you can say that negative charge can be easily converted into pi bond, and pi bond can be easily converted to negative charge. That is the basic idea. In this system, again, you can see that double bond separated by single bond, then double bond separated by single bond, then negative charge. Same type of system, that negative charge is separated by single bond, then double bond. Definitely, it's going to show the phenomena of conjugation. Again, you can see negative charge separated by single bond, then double bond. Definitely, this is the system. In the same way, negative charge separated by single bond, then double bond. Yes, this is the system. Negative charge separated by single bond, then double bond. Yes, this is the system. First type of system which can show the phenomena of delocalization. Just note down these important points. Now, there might be one question in your mind, sir, how can we say, like, in which direction these electron clouds are going to move? That is the most important question. So that part we are going to cover in the structural analysis of resonating structures. Okay, that part we are going to cover, how to write down the resonance structures, in which direction the entire electron cloud is going to move. But first of all, let's try to decode the type of system which can actually potentially show the phenomena of resonance. Okay. Now, if I talk about the second part, In second case, we have a double bond separated by single bond, then lone pair of electrons. So lone pair are just like negative charge. You can see double bond separated by single bond, then lone pair. Double bond separated by single bond, then lone pair. Double bond separated by single bond, then lone pair. In this case also, you can say double bond separated by single bond, then lone pair. Double bond separated by single bond, then lone pair. Double bond separated by single bond, and then lone pair. These are the systems of a second type of conjugation. I hope this part is clear. Just note down this important portion. Okay. Now, the next part is a very classical type of system, which is double bond separated by single bond, then double bond. This type of system. So in this particular case, you can say double bond separated by single bond, then double bond. Classical system. Double bond separated by single bond, then double bond separated by single bond, double bond separated by single bond, and benzene. Double bond separated by single bond, then double bond. Okay. Again, in this example, you can see lone pair is not going to participate because we have double bond separated by single bond, then double bond. So in this case, lone pair will not participate, because if this lone pair is going to participate, it's going to make chaos. Because if you can see, we have the system lone pair separated by single bond, then double bond. But after eventual structural analysis, you will find that both the double bonds are in front of each other. They are closer to each other, which will create hindrance. Okay. So this lone pair is not going to participate. Only these pi electrons are going to participate. Just like the system in this particular case, you can see double bond separated by single bond, then double bond, and just like that. We have the extended conjugation also. So in this particular case, you can see the phenomena of extended conjugation. If double and single bonds are separated to a large number of carbon atoms, it may be easy that you can find out the extended type of conjugation. I hope this part is clear. Just note down this important point. Okay. Now, let's talk about the next part, which is a pi bond separated by single bond, then vacant orbital. So we have double bond separated by single bond, then positive charge. Positive charge generally means we are talking about the vacant orbital. It talks about the vacant orbital. Positive charge means electron density is less. It means there is one orbital which is already vacant. So this type of system is also there. So double bond separated by single bond, then positive charge. Double bond separated by single bond, then double bond separated by single bond, and positive charge. Again, double bond separated by single bond, then positive charge. Again, the same type of system as well as the same type of system. So these are the next type of conjugated system. Just note down each and every portion related to the types of conjugation. After completing the types of conjugation, we are going to learn how this electron density is going to move and how can we write down different type of canonical forms as well as their resonance hybrid. Okay. If I talk about the next type of system, in that case, this is a very interesting system that we have double bond separated by single bond, then odd electron, or we know as free radical. This part is known as free radical. Okay. So you can see double bond separated by single bond, then free radical. Double bond separated by single bond, then double bond, then single bond, and then free radical. Again, in this case, same type of system, and same type of system. Just note down this portion. So you can see there are different aspects of these type of resonating structures. Okay. If you want, you can pause the video and write down each and every example so that you get to know about the idea that these type of systems can easily show the phenomena of resonance. And we know that this entire part is very vast. So definitely in every aspect of organic chemistry, we are going to use the phenomena of resonance, because different type of intermediates, different type of cations, different type of anions, they can actually show the phenomena of resonance. That's why this resonance is actually quite important. Okay. Now, if I talk about the basic rules to write down the resonating structure, how can we decode this entire part? So first of all, always remember that electron flow occurs from high electron density to low electron density. This is the most important part, most important part. Always remember, electron density flow will occur from high electron density to low electron density. It means I can say from lone pair to double bond, or you can say from lone pair to single bond. You can say from negative charge to single bond. You can say pi bond to single bond. Okay, this is the basic idea. Either you can say the electron flow will occur from lone pair to single bond, which is going to be converted into pi bond, and then negative charge to single bond, and then pi bond to single bond. So this type of phenomena is going to occur. This is the first part. This is the first part related to the entire analysis. Now always remember that negative charge can be converted into double bond. Okay, negative charge can be converted into double bond. Same lone pair can be converted into double bond. Okay, and double bond can eventually be converted into negative charge. Okay, so this is the phenomena which is going to occur during the conversion of the structure. Now, position of atoms cannot change, only pi electrons are delocalized. Always remember, there will be no change in the position. If the change in position is occurring, definitely that is different type of isomerism, which is basically known as tautomerism. For example, if I talk about this entire part, I can say we have a system that double bond separated by single bond, then negative charge. So negative charge can be converted into double bond, and double bond can be converted into negative charge, and electron density will always move from high electron density to low electron density. So negative charge is a free charge, definitely more electron density is there, so movement will occur from this side, and eventually it's going to be converted into the second type of structure. But in this entire case, you can see there will be no change in the position, only the pi cloud is changing its position. I hope this entire part is clear. I hope this part is clear. I hope this part is clear. Just note down each and every point. They are actually very essential whenever you want to determine the resonating structure. Okay. Now, the position of atom cannot be changed, only the pi electron can change. One example is this. If you look at this example, first of all, we have CH3, C double bond O CH3. In this case, this part is actually known as ketone. This functional group is known as ketone, which we already know. But if I talk about this entire part, you can see it has a double bond. So this is alkene as well as a combination of alcohol. So that's why the system is known as enol system. This system is known as enol system. Now in this particular case, you can see one hydrogen which is present on this position. If I talk about the structure, it may look like this. One hydrogen is present on this position. So what is occurring? This hydrogen is approaching this oxygen, and this double bond is changing its position, and eventually you can see the formation of this type of enol system. In which case you can see that hydrogen is changing its position. So I can say this entire part is not the resonance, but this entire phenomena is known as tautomerism. This entire part is known as tautomerism. Don't worry, we are going to discuss that part in the isomerism portion. Okay. So I hope this portion is clear. Second point is clear. Now let's talk about the next point. Second period elements should not violate the octet rule while drawing the resonating structures, and this point is a very important. Whenever any type of atom which is second period atom is involved in the phenomena of resonance, we know that it can only complete its octet, it doesn't have any vacant d orbital, so it cannot expand its octet. So always remember, whenever you are drawing these structures, always be careful that octet rule is being followed and it's not going to be hampered. Okay, so that is the basic idea. For example, if I talk about this system, that double bond is separated by single bond, then positive charge. So you may find that this can form resonance, that more electron density will go to that side, and eventually this carbon is going to get the positive charge. So this carbon is positive and this is the double bond. Now in this particular case, you can see that nitrogen is forming 1 2 3 4 5. Nitrogen is forming 5 bonds. If nitrogen is forming 5 bond, it means it has a 10 electrons in octet. It has a 10 electrons in its octet, which is next to impossible. It's not going to happen. It's not going to happen. So always be careful which type of system is going to show, but you need to make sure that octet rule is being followed. I hope this entire part is clear. Just note down this important point. Just note down this important point. Okay. In the same way, each resonating structure must have the same number of unpaired and paired electrons, because number is not going to change. Everything is same. You are just changing the position of a you are changing the position of a pi electron cloud. So it's not going to hamper the number of electrons which are present. So always remember, number of unpaired and paired electrons, they are going to remain same. They are going to remain same in the entire structure throughout. For example, if I talk about this structure, I can say in this particular part, if I am changing the structure a little bit, that it actually looks like this. It actually looks like this. So after the formation, you can see that we have initially one pi bond and 1 2. In between these cases, one free or odd electron. Okay. In this structure, again you can see we have one pi bond, and in this particular case you can see we have one odd electron. So this number is not going to change. This number is not going to change. But the main question which is coming in your mind, sir, how can we draw these structures? How can we decide the flow of the electron? So always remember, if one electron or any cloud is moving from one atom to another atom, always remember, if this is the situation that this part is giving electrons to this system, so this will acquire a positive charge and definitely this will acquire a negative charge. Okay, so donor species always gets a positive charge, acceptor species always gets a negative charge. Okay, so this is the donor always gets a positive charge and acceptor always gets a negative charge. Okay, it may be balanced in the entire equation or sequence, but always remember, donor is always going to lose the electrons. Definitely it will acquire a positive charge and acceptor is going to get the negative charge. I hope this entire part is clear. Now the next part is the net charge should be conserved in all the resonating structure. You cannot change the net charge. Definitely net charge is going to be conserved. It may change its position, but overall charge is going to remain same. For example, this type of structure, in this case you can see net charge is 0 because we have alternate double bond system. And I told you that this entire part, first of all, what is going to happen, that this bond is going to transfer here and this bond is going to go on this carbon atom. Now donor will get a positive charge and acceptor is going to get a negative charge. But again you can see initial charge was 0. Now we have 1 plus and 1 minus. So total charge, in this case net charge, is again 0. So charge is going to remain conserved. If your charge is not conserved, then definitely that is not the resonating structure you are drawing. Okay, I hope this part is clear. Now Next part is the stability of a resonating structure, and this is the most important portion. Like, what is the rules to decide the stability of the resonating structure? Because we know that different type of structures are going to be there. How to decide the stability? So there are certain set of rules by which you can decide that which structure is going to be highly stable. So first rule in that case is the resonating structure without any charge separation is actually highly stable. Just remember this point. If the actual charge separation, if there is no charge separation, the structure is highly stable. Okay, no charge separation means we are talking about the high stability of the structure. High stability of the structure. For example, just like the previous one, I can say I can draw the structure like this. For example, we have a CH2 double bond CH, single bond CH, double bond CH2. This is the first structure. If I talk about the second structure, it will be CH2 and it's going to acquire a positive charge, or let's say it's going to acquire a positive charge. Then we have a CH double bond CH2 and we have CH2 negative. Let's say we have this type of situation. We have this type of situation. CH and then CH2 negative. So we know in this second structure there is a charge separation. Definitely the stability of a first structure will be more. For example, this type of system, double bond separated by single bond, then double bond. Again, what you can do, you can delocalize this entire part and it will go on the oxygen atom and eventually it will become CH2 positive, then CH double bond CH and then O negative. This is the charge separating structure. Definitely first structure will be more stable in comparison to second structure. Just like this example, this is supposed to be CH2. This is supposed to be CH2. So in this particular case, you can see double bond separated by single bond, then double bond separated by single bond, then double bond. Extended conjugation is there. But again, you can change the electron cloud here. Then it's going to be go on this side and this is going to be converted into negative charge. Again, you can see in this structure that we have a CH2. Why I am writing this type of structure? Because double bond will be present here as well as here. So I can say that it's going to form a benzene type of structure and then O negative. Charge separation is there. Definitely stability of this structure will be more. I hope this part is clear. I hope this part is clear. Okay. The structure with complete octet of each atom is actually more stable, and you have to be very careful whenever you are dealing with the octet rule. In case of second period also, most important whenever you are dealing with second period elements. Most important whenever you are dealing with second period elements. And in this particular case, you have to make sure that each and every atom is going to complete its octet. So any structure with incomplete octet is highly unstable. For example, this particular part. If I talk about this entire analysis, we have double bond separated by single bond, then lone pair. Lone pair has more electron density, so it will go from this side and eventually it will go on this side. So what is going to happen in this particular case? And there is a positive charge also, and there is a positive charge also. Okay, so lone pair separated by single bond, then double bond which is separated by single bond, then positive charge. This is the entire system. So first of all, what is going to happen? First of all, in this structure you can see we have a positive charge here and then double bond here, and this is Cl having lone pair of electrons. This lone pair is going to be converted into double bond and this entire part is going to be converted into negative charge. So one structure which is going to form in this particular case will look like this, so that will be negative charge. This will be double bond Cl. Now donor atom always gets a positive charge, so this is the positive charge and again we have positive charge here. Now negative charge separated by single bond, then positive charge. Again this is going to participate in the resonance and eventually it's going to form the final structure which actually looks like this. Now in this case, if you see this positive charge, carbon is going to have only 6 electrons. In second structure again we have positive charge, it means 6 electrons. Now there is no positive charge on carbon atom, means complete octet. We have complete octet. It means in this particular case, I can say that the second structure is going to be more stable in comparison to the first structure. Okay, because chlorine's octet is always complete. Chlorine has excess of electrons. Again, you can see it is going to complete its octet. So every atom has completed its octet. Definitely that structure is more stable. Just have a look at it and note down. Okay. In the same way, negative charge on more electronegative atom is going to be more stable, and positive charge, if it is present on the less electronegative atom, is more stable. Because more electronegative atom means it acquires the electron density. It has the attraction towards the electron density. So negative charge will be more stable on the electronegative atom, and positive charge will be more stable on the less electronegative, or you can say electropositive atom. That is the basic part. That's the basic part. So you can see, if I talk about this structure, carbon is having the negative charge. So we have CH3, C double bond O, CH2, negative. So this is the situation. We have CH2 negative. If you see that this negative charge is going to go on this side, because we have the system double bond separated by single bond, then negative charge. It's going to get the double bond, and then it's going to get the negative bond. So negative charge is present now in oxygen, and carbon has complete octet. If I talk about the stability, always remember that this structure is having oxygen, which is more electronegative, and negative charge is present in more electronegative atoms. So you can say that negative charge is present on more electronegative oxygen atom. So definitely it's going to get much more stability. So second structure will be more stable in comparison to the first structure. In the same way, if I talk about the same phenomena, now oxygen, which is highly electronegative, is having the positive charge, which is highly destabilizing. But if I compare the electronegativity of oxygen and nitrogen, I can say nitrogen is less electronegative. So I can say positive charge on nitrogen, which is less electronegative, will be more stable. It's going to be more stable. I hope this entire part is clear. I hope this entire part is clear. So this is the basic idea about the structural analysis related to resonance. I hope this part is clear. I hope this part is clear. Now, you may find it very difficult that the rule of electronegativity and rule of octet, they are contradictory to each other. They are contradictory to each other. If any situation arises like that, one structure is having any electronegative atom with positive charge or any electropositive atom with negative charge, and there is one situation that there is a complete octet and incomplete octet, always give a preference to the octet rule. This is the most important part I want to mention, because it is slightly confusing. It is slightly confusing. For example, if I talk about this type of structure, that carbon is having positive charge and there is a double bond and lone pair. So you can see that this is going to be converted, this lone pair is going to be converted into double bond, and eventually oxygen is going to get positive charge. Now the basic idea here is that carbon, which is less electronegative, contains positive charge, and oxygen, which is more electronegative, contains a positive charge. So you may find that this structure is going to be less stable and this structure is going to be more stable. But in this particular case, as you can see, carbon has only 6 electrons. Carbon has only 6 electrons in this particular case. You can say carbon has only 6 electrons in this particular case. It means its octet is incomplete. But in this structure, you can see there is a complete octet of carbon. That's why second structure is going to be much more stable in comparison to first structure. Another example, in that particular case, you can see this structure, that we have OH, then we have a CH positive, then we have NH2. Now in this particular case, you can see either the shift will occur from this side or from this side. If this side change is going to occur, you can find it the structure like we have OH, we have we have OH double bond positive, then we have a CH, and then we have NH2. That is the structure. That is the structure. Okay. Now in this particular case, I can see we have 6 electrons of carbon in this first structure. In the second structure, we have 8 electrons on carbon. In third structure also, we have 8 electrons on carbon. So these two structures can be considered for the stability. Now this less electronegative atom is having positive charge, so it is more stable. In this case, more electronegative contains a positive charge, it is less stable in comparison to this. So second structure is highly stable than third structure, but because of incomplete octet, first structure is least stable. I hope this entire part is clear. I hope this entire part is clear. Just have a look at it. Just have a look at it. You have to write down each and every point so that you can understand what is going to happen in this particular phenomena. Okay, you have to write down each and every point. Okay, now let's talk about another rule. Always remember, two different compounds in which one compound has more conjugation is absolutely more stable, provided the nature of bonding is same. Okay, so whenever you are comparing two compounds, I told you that extended conjugation is actually very good. It's always much more preferable. So in this particular case, let's say we have the structure like this: CH2, CH, 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 CH2, CH, and CH2. So in this particular case, you can see double bond separated by single bond, then double bond separated by single bond. So conjugation is up to this entire part only. Conjugation is up to this part only. In next structure, you can see double bond separated by single bond, then double bond separated by single bond, then double bond, and then single bond. Extended conjugation is there. So you can see in the second structure, we have extended conjugation. We have extended conjugation. Definitely extended conjugation, which we will be much more preferable in comparison to less extended conjugation. So stability of second structure will be more in comparison to first structure. Okay, so there are multiple rules. I know that it's a slightly tedious job, but whenever you get more friendly with these structures, whenever you know how to draw these structures, you will be able to understand like which structure is going to be very stable and which structure is going to be highly unstable. Okay. Now, in two compounds, if one is aromatic, always remember aromatic gets the preference. Aromatic always gets the preference, and another is non-aromatic. Aromatic means we have a cyclic system where conjugation is present. Aromatic means generally we have a cyclic conjugated system. We have cyclic conjugated system generally. So in this particular case, always remember that conjugation is equal in both the compounds. Then aromatic compound is more stable. Make sure that nature of bonding is same. Okay, because whenever you are comparing, you need to make sure that the entire data is the same, but only one thing is going to differ. So if I am comparing aromatic with non-aromatic, because you can see we have 1, 2, 3, 3 pi bonds separated by 3 sigma bonds. 3 pi bonds separated by 3 sigma bonds. So number of bonds are exactly same, their nature is all, absolutely same, but this part is open chain, this part is cyclic and conjugated. Definitely this part is aromatic. Definitely this part is aromatic. Okay, so first of all, definitely this part is aromatic. If this part is aromatic, definitely you can say stability of aromatic compound will be more in comparison to non-aromatic one. I hope this entire part is clear. Okay. The structure with linear conjugation is more stable than cross conjugation. Okay. Make sure that the nature of bonding is the same, and it's a very interesting aspect. It's a very interesting aspect. What happens in this particular case? Let's say we have 1, 2, 3. 3 pi bonds are there and 1, 2. 2 sigma bonds are there. In this particular case, you can see 1, 2 and 3. 3 pi bonds are there and 2 sigma bonds are there. So nature of bonding is exactly same. But in this case, you can see that we have extended conjugation. We have extended conjugation. But in this case, there are two opposing forces, that one part is involving in this conjugation, and another opposing factor is also there, that this part is also involved in the conjugation. So if both the conjugations are merging together, if they are opposing each other, that part is cross conjugation. There are two directions for the conjugation part, but in this case there is only one direction. It's a linear conjugation. It's a linear conjugation. So definitely this part will be more stable in comparison to the cross conjugation part. I hope this entire portion is clear. Just note down each and every point. Just note down each and every point. Okay. Next part, compounds in which unlike charges are close enough, they are more stable and more contributing towards the resonance hybrid in comparison to those structures where same charges are closer to each other. Because same charges are going to repel each other, they should be far away from each other. Okay. So remember that same charges should be far from each other and opposite charges should be closer to each other. But the compound in which like charges are close enough, they are less stable than the compounds in which the like charges are far enough. Okay, this is the second point. This is the second point. I hope this part is clear. Just note down this point, that unlike charges should be closer to each other. It means we are talking about the stability of the resonating structure, and same type of charges, they should be far from each other. Then only we can say that the structure is going to be much more stable. Okay. For example, in this particular case, you can see that we have first OH, which is known as phenol. So this structure is phenol. In this particular case, you can see there is no charge separation. In this first structure, you can say there is no charge separation. So we have lone pair of oxygen. So lone pair separate by single bond, then double bond. Conjugation is going to occur. Now the donor atom will get a positive charge, acceptor will get a negative charge. Then again negative charge separate by single bond, then double bond. Again same type of conjugation. So what happens? This is going to like this, and this is going to move like this. Again in this case you can see double bond and then negative charge. Then again this system will become conjugated like this, and it will form the structure like this. And finally this negative charge is going to go on this side, and this pi bond is going to be converted into negative charge. So negative positive becomes 0. So that's why we have OH. Again in the last structure you can see no charge separation. There's no charge separation. You can see first of all that the structure 1 is exactly looking like the structure 5th, but there is only change in the bond position. Both the structures are going to be highly stable. So you can see stability of first and fifth is equal, and they are highly stable. These are highly stable. Okay. Now you can see in this particular case negative and positive charges, like charges are closer to each other. Positive and negative unlike charges are closer to each other, it means they are stable. And when the unlike charges are far from each other, it will be highly unstable or less stable, you can say. So the second and fourth structure are stable because unlike charges are close. You can say in this particular case, unlike charges are close. In this particular case, you can say unlike charges are close. So definitely stable. And least stable will be the third structure. I hope this entire analysis is clear. I hope this part is clear. Okay. Next part, which is the concept of mesomeric effect. So we have already completed the entire portion related to resonance, resonating structure, how to draw the resonating structure, and how to talk about their stability. Now the main application part in case of electronic effect is related to mesomeric effect. Always remember this part is much more prominent. This part is much more prominent in aromatic compounds. This will be very helpful whenever you are dealing with aromatic compounds. Although you can apply this phenomena in different aspects also, but it is much more prominent in case of aromatic compounds, or generally known as benzene derivatives. Mainly benzene derivatives. Although there are different type of aromatic compounds, but mainly we are focused on the benzene derivatives. Okay, when a group or atom, I can say when a group or atom, any type of a group or atom releases or withdraw pi orbital electrons, releases or withdraw pi orbital electrons in any conjugated system, then it is called mesomeric effect. And in this particular case, whatever group is involved is known as mesomeric effect group. Okay, so the group is mesomeric effect group, and this phenomena is known as mesomeric effect. So just like the inductive effect where the transfer of electron takes place via sigma bond, in this case this transfer is taking place through a pi bond. Okay, there is a push or pull of a pi electrons of the conjugated system of the molecule. Just note down this important point. Just note down this important point. Okay, just note down this important point. Okay, I hope this part is clear. Let's talk about the next portion related to mesomeric effect. Okay, so basically it's nothing but the pi electron pull or pi electron donation through a particular group or atom. Okay, now in this particular case, if I talk about the next part, always remember that AM effect operates only in the conjugated type of system, and now we know what is the basic meaning of a conjugated type system. So always remember, in this particular case we are talking about the conjugated system. In the same way that AM effect has no correlation with the electronegativity of the connecting atom of the group. It doesn't make sure that if the atom is highly electronegative and it has certain lone pairs or it has a double bond, so it's not going to donate that particular part. If it is involved in the conjugated system, definitely it's going to participate in the entire part. I hope up to that part everything is clear to everyone. Just note down this important point. Okay. Now, what about the M effect? Just like the inductive effect, we have a plus I group as well as minus I group. Plus I groups are those groups which can donate the electron density via sigma bond, and minus I groups are those groups which can attract or withdraw the electron density via sigma bond. So just like that, we have a plus M as well as minus M group. Plus M groups are those groups which can donate the electron density via pi electron cloud or via conjugated system, and minus I group minus M groups are those groups which can withdraw the electron density via pi electron cloud or via conjugation. So in this particular case we are talking about the first part, which is electron releasing groups. So in this particular case we have oxygen negative charge, because it has lone pairs, definitely it can participate. Then we have NH2 type system, then we have NHR type system, then we have NR2, then OH, OR, NHCOR, OCOR, PH, FCl, BRI, NO as well as CN type system. But in this particular case, always remember, whenever we talk about these halogens, in that case their inductive effect is much more prominent in comparison to their plus M effect. In that case, always remember, they can withdraw the electron density just because of their higher electronegativity, but they cannot show that type of M effect in case of conjugated type system. Okay, so this is the actual table which depicts the actual analysis. Okay, in the same way we have a minus M group also, but if I talk about the plus M group, we need to understand what is the effect. So for example, I am talking about the phenol. In case of phenol, you have OH group and this has lone pairs. So definitely it can donate the electron density to the conjugated system, which is benzene ring in this particular case. And what happens in this particular case? You can say that we have the first type of structure. Whenever you are representing the resonating structure, you can use double-sided arrow, which is used to represent the resonating structures. In that case, first structure will look like this, that we have negative charge. This is OH positive. Then this negative charge is going to go and it's going to form double bond OH positive, double bond negative charge, double bond. Then again it's going to participate and eventually it will form a structure like this, negative charge, double bond OH positive, and eventually the final structure looks like this, OH. I hope this part is clear. Now the main question in this particular case, that if I talk about mono substituted benzene, that there is a substitution on the benzene ring on one position only. For example, if I talk about this entire part, this is the benzene ring and one substitution is present, which is the mono substituted benzene ring. So you can see that carbon which is attached to the substituted part or group, any of the group which is attached to that carbon, the next carbon or that next position is actually known as ortho position. So this part is ortho, this part is ortho position. So there is one thing which is related to ortho and para directing groups. So in this particular case, this position is ortho position. The next position is actually known as meso position. Sorry, meta position. Next position is meta position. Meso is a type of compound which we are going to discuss in case of optical isomerism, chiral carbons. Okay, and the next position is basically known as para position. Next position is known as para position. Now in each type of transfer, you can see that electron density is going to increase on ortho position, first part, then it's going to increase on the para position, then again it's going to increase on the ortho position. So this plus M group is going to increase electron density on ortho and para positions. A very interesting observation in that particular case. It's going to increase the electron density on ortho as well as para position. Just note down this important point. Just like that, if I talk about the next part, we have minus M effect. So all those groups which can withdraw the electron density towards themselves through pi conjugation are basically those groups, and they are going to show minus M effect. This is a clear-cut example that this pi cloud is going to go on this carbon, this pi cloud is going to go on this particular carbon, and eventually it can form. If I talk about the actual structure, just look at the structure. We have a carbon, double bond carbon, single bond carbon, double bond carbon, then a particular group. So this pi cloud will shift on this side, this cloud is going to shift on this side. It means this group is attracting the electron cloud, pi electron cloud, via conjugation. This effect is a minus M effect, and again in case of benzene ring, you can see this type of analysis. We have certain groups which can show minus M effect very easily. There are certain groups which can show minus M effect very easily. For example, if I talk about the example of nitrobenzene, in case of nitrobenzene, you can see this type of clear-cut example. If I talk about their order or their strength, you can say NO2 is actually very strong in that particular case. Then we have SO3H, then we have CN, CHO, C double bond O, then we have COX, anhydride part, then we have ester type of part. So this is the oxygen, sorry, typo error. Then we have COH as well as CONH2. What happens in each case? What happens in each case? You can see, if I talk about the example of nitrobenzene, then we have nitrogen, double bonded oxygen, and then one oxygen which is coordinated. Now in this particular case, what happens? We have the system double bond separated by single bond, then double bond. So eventually this is going to be in conjugation. Donor atom will get a positive charge, acceptor will get a negative charge. So the first structure will look like this. We have a positive on this side, double bond N, and then we have O negative, and this is the coordinate bond. Okay, this particular part is going to occur in this particular case, and then we have rest of the system same. Then double bond separated by single bond and positive charge, again conjugation. So electron density will move from higher electron density to lower electron density. In this particular case, you can see the next structure will look like this: positive charge, double bond, double nitrogen, and then we have O negative, and then we have oxygen here. Again, in this case, the electron density is going to shift like this, and eventually it's going to form a structure: positive charge here, double bond, nitrogen, O negative, and then O like this. Again, you can see what is going to happen, that this entire part is going to occur on this side, and this negative charge is going to move back to the original position, and it will form a structure like N, double bond O, oxygen, then you have double bond here, and double bond here. Now what is happening in this particular case? You can see that positive charge means less electron density. So in case of minus M effect, always remember that electron density is going to decrease on ortho and para positions. Okay, so it is exactly the opposite part of plus M effect. So in this particular case, electron density will reduce on ortho as well as para position in case of benzene. In case of mono substituted benzene. I hope this entire part is clear. This is the basic idea about plus M group as well as minus M group. Next part is basically the applications part of resonance, and they are very, very interesting and they are very wide. Definitely in case of a simple aliphatic, simple alkene type system, simple alkyne type of system, simple conjugated type of system, dienes, diions, in case of aromatic system, you can see the applications of resonance. So first part is basically the stability of a reaction intermediate, in which the reaction intermediate we are considering is the stability of a carbocation. If somehow the carbocation gets more electron density, it means we are talking about the stability of that particular carbocation. More resonance in carbocation means more stability of the carbocation. Aromatic cations are more stable than the non-aromatic cations, just because this positive charge is going to be uniformly distributed in the entire structure. So always remember that resonance is going to stabilize the entire carbocation system if it is applicable. Okay, for example, if I talk about these parts, that we have a CH2, CH, CH2. So double bond separated by single bond, then positive charge. You can see the phenomena of resonance. Definitely in this particular case, if I talk about CH3, CH2, CH2 positive, it is basically 1 degree carbocation. 1 degree carbocation. If I talk about this type of system, which is a CH2, CH, CH2, CH2 positive, it is a positive charge 1 degree carbocation, but in this particular case this CH2, CH2 system is present, which is going to withdraw the electron density because it is not in conjugation. So in this case you can see electron density will go towards this side because of its plus I effect. It's a plus I effect, but we know that this entire group shows minus I effect. So it can withdraw the electron density towards the other carbon atoms. So when the electron density again decreases in the carbocation, it becomes highly unstable. Both are being 1 degree carbocations, but in this case electron density is withdrawing and electron density is giving in this particular case. So this is more stable, this is less stable, and this is highly stable just because of the conjugation. Okay, so conjugation provides more stability. For example, this entire part, you can see only one conjugated system is there. Extended conjugation, very much extended conjugation system, or you can say aromatic system. Aromatic system is highly stable because positive charge is going to be delocalized in every part, which provides more stability. More resonating structures means more stability. So in this case only one structure is possible, in this case two structures are possible, in this case multiple structures are possible. That's why it is more stable. For example, if I talk about the structural analysis, in this case you can see only one structure is possible, which is like this. So you have CH2 and now it becomes 2 degree carbocation. 1 degree is converted into 2 degree, which is more stable. In this particular case, what happens? First of all, this is going to occur. So you have a positive here, double bond CH2 and then again double bond. So what happens? You can again draw one structure. One more structure is there. It's going to look like this. So you have a positive here, double and then double CH2. Okay, two structures are possible, more stability. In this case, you can see that we have the first type of structure which looks like this, positive here, double bond CH2, and then next structure looks like this. Just draw these structures, okay, they are very important. CH2, and the next structure looks like this. You have a positive here, double bond here, double bond here. Sorry. The next structure looks like this. You have double bond CH2, then you have a positive double bond here, double bond here, and finally you can draw one more structure that this positive charge is there and double bond is going to change its position. So one more structure is there. So you can see one, starting with this particular part, 1, 2, 3, 4 and 5. 5 structures are possible in that particular case. I'm not writing the last structure, but you can write down the structure by yourself, that this double bond is going to go on this side and positive charge will be acquired on CH2 again. Okay. So that's why it has more stability. I hope this entire part is clear. Just note down this important point. Okay. If I talk about the stability in these type of compounds, now they are very interesting. In this case, you can see we have again carbocation aromatic system, but in this case NO2 present. NO2 means in this particular case it has minus M effect and it is closer. Definitely its minus M effect is actually much more prominent. It's going to withdraw electron density very fast and carbocation stability is going to decrease further. When this is present on the meta position, always remember 1 or 2 points you need to understand in this particular case. 1 and 2 points you are going to understand in this particular case. First part, if any type of a group is present, always remember that the Mesomeric effect is distance independent. It is distance independent in nature. Okay, because it talks about the extended conjugation, it's not going to matter. It is distance independent. On meta position, we can only see plus I or minus I effect. I'm going to tell you the reason also, but note down this important point that on meta position, because with respect to this position, this is the mono-substituted carbon in the aromatic ring. This position is ortho, this position is meta. So on ortho position, it's going to show plus M and minus M. On meta position, only plus M, only plus I and minus I are going to work. No mesomeric effect is going to work on this particular position, because it's not going to hamper this entire carbon directly. Okay. And again, in para position, you can see that this effect is going to work. So in this case, only minus I effect. In this case, minus M effect will be working. Okay. Now, along with M effect, definitely nitrogen, which is more electronegative, is going to show minus I effect. So minus I effect is there, as well as minus I effect is there. But we know that inductive effect is distance dependent. So in this case, minus I will be more prominent because it is closer to that carbocation. But in this case, it is far from the carbocation. So minus if I will not be that prominent. Okay. Now let's talk about the structural analysis. For example, I'm starting with this part. What is going to happen in this particular case? Let's say we have NO2. So this is the coordinate bond, this is the double bond, and then we have CH2 positive. This was the original structure. Okay, this was the original structure, or you can change the layout little bit, just like the original structure. You may be confused, so that's why I'm writing the actual structure. Then we have N oxygen coordinate and double bond oxygen. This is the situation. So what is going to happen? First of all, that this double bond is going to move towards that carbon, and eventually it will form double bond CH2, then positive charge directly in contact with oxygen, and then rest of the groups are same. Now again, double bond separated by single bond, then positive charge. Now what happens in this particular case? You can see this type of structure might occur. So in this particular case, you can see that we have one structure, double bond N, coordinated oxygen, and then oxygen positive is there, which is highly unstable. Positive charge on oxygen is a highly unstable. Okay, that's why whenever it is near, definitely it's going to show minus M effect. It's going to withdraw the electron density, but eventually what happens, that it's going to create a chaos. This is the first part, when this entire part is involved in the conjugation, when positive charge is involved in the conjugation. Another explanation is there, that let's say I'm drawing this structure. And we have an O double bond O. So if I talk about this part, it's going to withdraw the electron density, pi electron density in the first case, and it's going to acquire the negative charge, and we have a CH2 positive already present. So what happens if it is going to show its M effect? What is going to happen in this particular case? You know that we have a situation which is CH2 positive and then again positive on this carbon. We have nitrogen coordinated, oxygen negative, and then we have this type of situation. Now you can see in this structure, two positive charges are closer to each other. Positive charge only gets stabilized when something is there to give its electron density. If something is withdrawing its electron density, it will be highly unstable. Two like charges are there, definitely this structure is highly unstable. Highly unstable. Okay, so if it is showing minus M effect, it's going to directly hamper the carbocation. Now let's say in the third case, I have this situation like this. Like the previous structure, you can see we have an oxygen, double bonded oxygen, then we have a CH2 positive. Okay, if it is showing its minus M effect, what's going to happen? That this part is going to move on this side, this part is going to move on this side, and eventually you will see the structure which looks like positive charge here. Then you have double bond nitrogen, oxygen negative, oxygen negative in this particular case, double bond, and CH2 positive. Next structure will be like this movement, and you can see the structure looks like this. Positive charge here, double bond, double nitrogen, coordinate and O negative, and then double bond and CH2 positive. So this positive charge is again far from that positive charge. It is not coming directly in contact. In the third structure also, what you can do? In the third structure, you can see that we have a situation like this, that now we have double bond and then CH2 positive charge will be there, double bond N, and we have one coordinate oxygen and oxygen negative. This is the structure. In every structure you can see there is one moiety, that this CH2 positive separated by single bond then double bond is intact, which provides extra stability. We have a CH2 positive separated by single bond then double bond, one moiety is there. Double bond, single bond, positive charge, one moiety is there. Double bond, single bond and positive charge, one moiety is there to provide the stability. So positive charge is not coming directly in contact with the cation. So in this case, when this NO2 group is present on the meta position, it will not affect the carbocation via minus M effect. Only its inductive effect is going to work just because of the difference in electronegativity. So always remember, this is the basic idea. Write down each and every structure. This is the basic explanation. Okay. So finally you can say that the highly stable carbocation will be the second carbocation, because only minus I effect is working in this particular case. This case minus M is working, this case minus M is working, and it is distance independent. But minus I is a distance dependent. It is highly applicable in first case but least applicable in the third case. So you can say second is stable, then third, and least stable will be 1. I hope this entire part is clear. Okay. Now if I talk about the next part, again you can talk about the stability order of these three carbocations. OCH3 is there having lone pair. It has plus M effect but minus I effect because oxygen is there. It has a plus M effect but minus I effect. In this case, it has only minus I effect. In last case, again para position means it's going to show plus M effect but minus I effect. M effect is distance independent but I effect is distance dependent. So one part is a donating effect, one part is a withdrawing effect. If donating effect is more, then definitely carbocation will be stable. So in this case, donating effect is more but withdrawing effect due to large distance is negligible. So third carbocation is highly stable, then first carbocation, and then second carbocation. So the final order of stability will be third, then first, and then second. I hope this entire part is clear. I hope this entire part is clear. Okay. Just like that, if I talk about the stability of a carbon ion, it is exactly opposite to carbocation. It is exactly opposite to carbocation. So you can simply say if it is exactly opposite to carbocation, it means in this case minus M effect is going to increases the stability and plus M effect is going to decrease the stability. I hope this part is clear. I hope this part is clear. Because the negative charge is more stable if the negative charge is decreases by any other effect. If it is going to increase the negative charge again, definitely the system will be unstabilized. For example, if I talk about this entire part, negative charge separated by single bond and double bond. So what happens? Definitely it's going to participate in the conjugation. In this particular case, negative charge is directly present on the double bond, highly unstable type of system, and then negative charge separated by this entire part and having plus I group, okay. So in this case, negative charge is actually destabilized by plus I effect, because electron density is going to increase. This becomes highly unstable. First part, just because of the resonance, becomes highly stable, and second part is in between, because negative charge is present on the electronegative carbon. Double bonded carbon is more electronegative. Triple bond carbon is much more electronegative than double bonded carbon. So electronegative atom contains negative charge, is slightly stable. Okay, so I hope this part is clear. So first, then second, then third. This is the stability order. In the same way, if I talk about this entire part, again you can see instead of carbocation, now we have used the carbon ion. In this case, if it is present on the ortho position, definitely it will show minus M effect first of all and minus I effect. On meta position, only minus I effect. On para position, we have minus M as well as minus I. But because minus I is a distance dependent, it is much more in ortho position, less in para position. So more stability will be first part, because every electron density is actually reduced by withdrawing of this NO2 group. So you can say this one will be highly stable. Then the third part, because minus M and minus I both are working, and second part is least stable because only minus I is working in this particular case. So that will be the stability order. So that's how you can deal with different type of groups which are present, and you can talk about the stability of carbocation and carbon ion which are present. Okay. If I talk about this entire part, again you can see in this case, because we have a plus M effect is there and minus I is there. In this case only minus I is there. In this case plus M and minus I. So plus M effect means destabilization. It means destabilization. So these two are going to be destabilized and this one will be highly stable. So first of all, the maximum stability is of second. Now how to decide first and third? Because minus I is a distance dependent, it is working much more in first case. So it can withdraw electron density more in comparison to this part. So third will be highly unstable and moderate will be first. I hope this entire part is clear. Very interesting phenomena related to the resonance. Okay. In the same way, if I talk about the free radicals, just like any other part, just like carbocations, same as carbocations, entire theory of a free radical is just like carbocation. Okay. Just like carbocations. So for example, if I talk about first part, CH2, CH2 free radical. So definitely this will participate in the resonance. Then CH2, CH free radical. Free radical directly present on the double bonded carbon. In this particular case, I guess the structure is not that correct. I am again writing the structure. It's a typo error. Sorry. It's a typo error. So I am again writing the structure. First structure is CH2 double bond CH, then CH2 free radical. This is the first structure. Next one is CH2 double bond CH free radical. This is the second structure. And third structure will be CH2 double bond CH, then we have a CH, then we have CH double bond CH2, and this part is free radical. This is the third structure. Okay. In first structure, you can see conjugation from one side only, from one side. In second case, no conjugation, no conjugation. In third case, you can see cross conjugation. Means from both side, from both side. This free radical is stabilized from this side also, this free radical is stabilized from this side also. It means this has maximum extent of delocalization. You can see, if you want to explain, this will be like this will be like this. So half electron movement means half arrow, okay, and this will be like this. So first structure in this particular case will look like CH2 free radical, then we have a CH double bond CH, then we have a CH double bond CH2. Extended conjugation system. Next part, it may be possible that it will go to this side. Next part will be possible that it will go to this side. This will come this side and this will come this side. And it will form the next structure, which is CH2 double bond CH, then CH double bond CH, and then CH2 free radical. So both the parts are going to provide stability. Definitely that part will be more stable. So third part will be highly stable. Second part will be least stable, because this carbon is electronegative carbon and it contains less number of electrons. Definitely that will be not the case. It is highly unstable. I hope this entire part is clear. I hope this entire part is clear. And that's how you can deal with different type of analysis. You can deal with different type of analysis related to the stability of carbocation as well as carboanion and free radicals. There are certain concepts which talks about the stability of acidic strength, or I can say the acidic as well as basic strength. That part we are going to discuss in the next class. And don't worry, in next class also we are going to discuss numerous type of questions which were asked in the previous year examination related to the stability of carbocation, stability of carbanion, free radicals, and each type of electronic effect. So we have left with only two parts. First one is hyperconjugation, and next part is electromeric effect. That part will be covered in the next class only. Okay, so I hope everyone enjoyed this session, learned something new from this session. Remaining part we are going to discuss in the next class. Okay, so that's all from my side. Thank you so much.